We have another one, your metallic rod. It also fits into this particular two examples, so meaning that these two are the main examples of what? Your conductor. If you look at your copper wire, you allow easy free movement of what? Electrons and what? Heat molecules. While your metallic rod will also allow easy free movement of your what? Of electrons and what? And heat particles. Now let's move straight into an insulator. An insulator. What is an insulator? An insulator is automatically the opposite of what? Your conductor. What does that mean? It is any material that disallows totally the free movement of what? Electric charges through it. What does that mean? It doesn't allow movement of electrons. It does not also allow movement of what? Heat particles. Which means that if I have a log of wood here now, if I'm holding a log of wood, if I decide to what? Put this log of wood into an electrical field. What do I mean by an electrical field? A place where what? A region where electric charges are being experienced. There will not be movement of, I can hold this particular wood here. Now, these electric charges are being experienced here. They are being in contact with the wood. But because this wood does not allow movement of charges, there is no movement. So definitely, I won't be electrocuted here. Meaning that a wood is not what? Is not an example of what? It does not allow movement of electric charges and heat particles through it. So that particular phenomenon made this wood a what? An insulator. So that confirms our definition, which says that what? So as we're saying, we said a wood. Now this particular wood, because of its what? Refusal of what? Of allowing electrical charges to pass through it, and what? Heat particles to pass through it. That particular act will make this wood an insulator. So that is the proper difference between an insulator, which is a wood, and what? Your conductor, which is what? A metallic wire. So let's go to the last one, which speaks about your semiconductor. So these are classes of solid with electric resistance between that of a conductor and what? An insulator. That one is just straightforward. It has little or more characteristics of what? A conductor. And at the same time, it has characteristics of what? An insulator. So that is why they call it what? Insulator. That's why they call it what? A semiconductor. A semiconductor, meaning that it has traits of what? Acting as a conductor, and at the same time, little traits of what? Acting as an insulator. So those are the three major definitions of what? Insulator, conductor, and what? Your semiconductors. So let's go straight into electricity properly now. At this junction, we'll be looking at a lot of things as regards the experiences of the electrical charges, how to calculate them, how to eventually understand what is going on in totality in your what? Electrical field. So we'll be starting this particular series by going to another very interesting subtopic, which is termed electricity, current electricity. What does that mean? Current electricity. Now we are gradually going to electric field properly. So under current electricity now let's go into the introduction. It talks about, in our previous lessons we learned about charges at rest, but in this series we'll be looking at current electricity that we're dealing with charges in motion. Now initially, if you recall, when we were speaking about those charges, we defined a charge as what? An electric current or an electric charge parameter that does not move. It stays at a particular point. But at this junction, under current electricity, we'll be looking at those charges in terms of what? Their motion. That is, in terms of movement. When they move, it is when they actually move that what? Electricity will be what? Experienced. So those are the things we'll be talking about. Now, first of all, we'll start with electric current. We'll be looking at the actual meaning of what? Electric current. The actual meaning of electric current, potential difference, and resistance. Electric current, potential difference, and resistance. So now let's start with electric current. Number one, your electric current. Now, electric current is denoted by I in physics. It is denoted by I, electric current. Now, we also said we're looking at what? Your potential difference. Potential difference is denoted by what? V. Now, the last one we're looking at your what? Your resistance. Your resistance. Now, the resistance is denoted by what? R. So we'll be looking at your current, which is I, your potential difference, which is V, and your what? Resistance, which is what? R. Now, starting with current. A current is any motion. A current is any motion of charge from one region to another in a what? In an electrical circuit. What do you mean? Point A. Do you understand? This is point B. Now, the movement of this electron is actually from here to here. Now, it is actually when they move. Do you understand? When they are in motion, that will call them what? A current. That's just the practical definition of what? Electrical current. Now, in any electrical circuit, there is need to measure the following. Now, if you now have a circuit, let me give you a graphical representation of what we mean by a circuit. You can decide to put your battery here. Let's say this is your battery. Now, your battery is actually being connected to a lamp. This is a lamp. Now, at this region, let's say you connected it to an ammeter. Now, later, you now what? Lock it up here. Now, this particular diagram is called what? Electrical circuit. Your electrical circuit. So, when you experience movement of what? Charge along this electrical circuit, that charge that is actually been moving is now what we call your current. Hope you are getting it. So, when you have a circuit that allows movement of what? Electric charge, which is your electron, to move around it. Now, that movement of that electrical charge will make what? It will make it what? A current. Now, at this instance now, when you now have your electrical circuit, three things need to be known, as it needs to be measured here. You must measure your current, which is being measured by your what? Ammeter. This is your A. So current is measured with what? Ammeter. You also have to now, we must measure your what? Your EMF. That's your E. Your EMF is being measured with your what? Your voltmeter. You have your voltmeter, and you have your what? Resistance. Your resistance is being measured with what? Your resistor. So you are measuring current. If you measure current, you will be making use of what? Ammeter. If you measure EMF, you will be making use of an instrument called voltmeter. And if you measure resistance, you are making use of what? Resistor. So these are just the analysis of what? Electrical current, current electricity, and how far we are going to go. So let's proceed to current properly now. Let's start. We said we're going to start with current electricity. So the mathematical definition of current now, it says an electric current is the rate of flow of charges in a what? In a circuit. Now, when you have, this is a circuit, and now a circuit initially, the rate of what? Flow of what? Charge in that circuit is what we call what? The electrical current. So meaning that mathematically, I will be given as what? Q. Are you saying it? Q, which is your what? Coulomb. Which is your what? Charge. Your Q is what we measure the what? Charge. What does Q mean? Current, as in quantity of charge. Q means quantity. Quantity of what? Of charge. So Q. Now we now say the movement of what? charge with respect to what? Time. So it will now be over what? T, which is your what? Your time. Now mind you, this charge is measured in coulomb, while your T is measured in what? Seconds. So my current now is what? Q over what? T. Now mind you, the SI unit of current is now what we call what? Amps or ampere. Is the full meaning, then the shortest form is what we call amps. So these are the mathematical definition of what? The electrical current. Discharge over time. So you can now restructure your formula as well. Q equals what? IT. This is the general formula of what? Quantity of what? Charge. Equating to current and what? And your time. So that is number one definition. When we come to when we are talking about current, when we are talking about electrical current. So, but before we proceed, let's still talk about electrical current a little as regards their SI unit. I told you that initially the SI unit is ampere. Current is measured in amps. But we need to understand that when you talk about amps, your current now could be super twisted as regards the what? The minuteness. Let me say they can give you 2. If you have 2 milliamps, what does milliamps mean? It means that it is